Today I'm going to talk about a concept in digital logic design called an adder. So how do you add over binary operations? For example, let's suppose you have two inputs A and B and you have two outputs, their sum and their carry. So the way you add binary numbers is you have 0 and 0, the output is 0, which is the sum, and the carry is also 0. And let's suppose if you have 0 and 1, then the sum is 1 and the carry is 0. But if you have both binary numbers as 1 and 1, then you have sum as 0 and the carry as 1. So in digital logic design, you have to convert these truth tables into actual circuits. So the steps in doing so are, let's suppose you take this output, which is the sum, and see which binary numbers are 1, and see the corresponding inputs against the sum, the bit which is actually 1. So as you can see, S is 1 for 0 and 1 and 1 and 0. So if you write this in the form of an equation, this would be the case. S is equals to A dash B plus AB dash, which is actually a compressed form of an XOR gate. So we will write as A XOR B. And the circuit corresponding to this equation will be S is actually the XOR of A and B. Then we take the second input, which is the carry. As we can see that it is logic 1 only for the case of A and B inputs when they both are 1. So this corresponds to the equation C is equals to AB. And as you can see that AB is just an ANDing of A and B. So this is the circuit for the carry. When you combine both of them, so this is the final circuit for an half adder, where you take A and B as the input, their XOR is the sum, and for A and B, their AND is the carry. Now we will talk about the full adder. So in full adder, we have three inputs, A, B, and carry in, and we have corresponding two outputs, sum and carry out. So now we'll do again the same thing. We will derive a final circuit from this truth table. So how will we do that for the sum? We will see all the bits for sum which are logic 1 and see the corresponding outputs for that bit. For example, S is logic 1 for A dash B dash C in, then it is logic 1 for A dash B C dash, then it's 1 for A B dash C dash, and finally it's logic 1 for A, B and C. Now we will write that in the form of an equation. Here you can see that. We can reduce this equation further by taking common C in and C in dash from two of the expressions, and it will reduce to this form. And then as you can see over here, A dash B dash plus AB dash, which is actually an expanded form of XOR of A and B. So you'll write it like this. Similarly, this is an expanded form for XNOR between A and B. So finally, our equation will be an XOR of A and B, and then XORing that with C in. And the circuit would look like this, where we take AB, XOR it, and then we XOR the output again with C in and get the final sum. We will derive the circuit for the second output, which is the carry out. So we will see the carry out is logic 1 for which of the corresponding inputs? It is 1 for A dash B C, then it is logic 1 for A B dash C, and then it is 1 for A B C dash, and finally it is logic 1 for A B and C. When we write it in the form of equation, this is what we get. Again, we can reduce this equation in this form, and finally what we get is that you can XOR the input A and B and then AND it with the third input, which is the carry in, and then you can OR it with A and B, which is the AND of A and B. So the final circuit for the full adder will look like this. You will get the sum by XORing A and B, and then XOR the output with the third input, which is the carry in, and get the sum. And you get the carry out by taking the XOR of A and B and then passing it through the AND gate with the third input, and then OR it with the AND of A and B.